Good morning everyone. In this session, let us continue the last concept, that is decision trees. In decision trees, we have discussed what is decision tree and what are the important terminologies related to the decision tree, and also we have calculated two techniques, that is entropy and information gain. So in this session, let us discuss about the Gini index, that also used for the finding the impurity in a data set. And we know that, I'll just recap the last session, that is we find the entropy. The entropy formula is something like this: minus probability of S log of base 2 probability of S minus probability of no log of base 2 probability of no. And information gain is something entropy of whole data set minus weighted average into entropy of each feature. The same example, the same formulas, we have seen one example on this particular data set, that is given 4 attributes or features, then a person can go for play tennis or not. For that, we have seen how to find out the entropy of the whole data set, entropy of each feature, and also information gain for this particular attribute or feature outlook. We got something the value. Likewise, the information gain, we have to find out the 4 attributes. After finding out, we got that outlook is the highest information gain, so that will be taken as the root node. In this outlook, we know that we have 3 values, one is sunny, overcast and rain, so that we are going to split. And again we are going to find out the entropy and information gain of sunny, overcast and rain, and at last we are going to reach to a final decision tree. That is, you can see here, if outlook equal to sunny and humidity equal to high, yes, we can play for tennis, and if outlook equal to sunny and humidity is equal to normal, play tennis equal to yes, and if outlook is overcast, then directly we can say that play tennis equal to S, and outlook equal to rainy and wind equal to strong, no, there is play tennis equal to no. If outlook equal to rain and wind is weak, yes, play tennis equal to yes. In this way we are going to derive the decision tree. Here we get a question, like we can ask ourselves a question, that when we are going to split this particular splitting the decision tree. So when we stop growing this decision tree, usually we know that the real world data sets have large number of features which will result in a large number of splits, that is, which in turns gives us a big huge tree. So such trees can take much time to build, and even there is a chance of leading to the overfitting. That means the tree will give very good accuracy on the training data, but it will give bad accuracy in the test data. That is what we call it as the overfitting. So there are many ways to tackle this problem. One, that is through hyperparameter tuning. Let us see how we are going to do the hyperparameter tuning. Since we can set the maximum depth of our decision tree using the max depth parameter. See, if our tree is growing till some depth, so we can keep a limit over there, that max depth equal to some value, then we can stop growing our decision tree. This is one of the parameter, that is max depth. So the more the value of max depth, the more the complex will be. But training error will of course decrease, but we increase the max. If we increase the max depth value, obviously training error will decrease, but when our test data comes into the picture, now we will get a very bad accuracy. So hence we need a value that will not overfit as well as underfit our data. For that reason, we are going to use a parameter called as max_depth. Next, another way is to set the minimum number of samples of each split. That is, simply we are going to use a parameter called as min_samples_split. Here we can specify the minimum number of samples required to do a splitting. So that we can simply write it as min samples underscore leaf, another parameter. Here it is splitting, here it is min samples underscore leaf, represents the minimum number of samples required to be in the leaf node. The more you increase the number, the more is the possibility of overfitting. That's why we should reduce, or we should decrease the minimum samples leaf. And then max features. It helps us to decide what number of features to consider when looking for the best split. This is also one of the way to hyperparameter tuning. Then another method is called as the pruning. We know that this pruning is that can help us avoiding this overfitting. It helps in improving the performance of the decision tree by cutting the nodes or sub nodes which are most significant. And there are mainly two ways that pruning, that is, one is pre-pruning and one is post-pruning. The name itself indicates that we can stop growing the tree earlier. That means we can prune or remove or cut a node if it has low importance while growing a tree. When we are growing a tree, if we feel that some feature at some point of time there is no less value or less importance, there itself we can prune that particular subtree. Then next one is post pruning, that is, once our tree is built to its depth, okay, we can start pruning the nodes based on their significance. Okay, this is called as the post pruning. So these are the some of the hyperparameter tuning we can do when we are constructing some application with the help of decision tree, mostly to avoid the overfitting problem. Next, we have seen two methods, entropy and information gain. Both are used for which attribute in a particular data set or feature which we are going to take it as a root node. Based on the information gain, which is having the highest information gain, that particular feature or attribute we are going to take it as a root node. Similarly, along with entropy and information gain, we also have an other method called as the Gini index. So what is this Gini index is? It measures impurity or inequality frequently used in decision tree algorithms. Even this is also used to decide out of all features which feature we are going to take it as the root node. So it quantifies the probability of misclassifying a randomly chosen element, that is, if it were randomly labeled according to the distribution of labels in a particular node. And the equation for Gini index is something given like this: Gini index equal to 1 minus within the brackets p1 square, p2 square, so and up to pk square. So what are these p1, p2 are the probabilities of each class in the node. So this is the formula how we are going to find out the Gini index. See, when this is the visualization how we are going to construct a decision tree using the Gini index. See, here we have a data, and for that, first thing is we need to get the data set. After getting the data set, the very first thing, if you want to construct the decision tree using Gini index, is first we need to find out the Gini index, that is by making use of this formula. Then along with that we also should find out the weighted Gini index, where we have these all terminologies. I will explain now. We have to apply this, then we are going to take a decision like whether it should be, take the same example like earlier, we can go for play tennis, yes or no. Then at point of here we are going to take the decision. So this is how a decision tree can be constructed with the help of Gini index. Next, the same here, the formula what we have written here, weighted Gini index. In that, this Gini A of D represents the weighted Gini index of the entire data set, and it is going to be divided it into two subsets, that is D1 and D2. And in that we have N1, that is number of instances in a subset D1, and N2 is the number of instances in the subset D2, and N is the total number of instances in the entire data set, that is D, we can give it as N equal to N1 plus N2. And similarly Gini D1 and Gini D2, this is the Gini index of subset D1, okay, which quantifies the impurity or uncertainty of class labels in D1. And similarly Gini of D2, this is the Gini index of subset D2, similar to the Gini of D1 but for the other subset. Means the whole data set we are going to divide it into two subsets like D1 and D2, and in that data sets we are going to find out the impurity or uncertainty of class labels. So these are the some of the concepts related to this weighted Gini index. So the same data set what we have seen earlier, like finding out the entropy and information gain, the same data set I have taken here, and for this data set let us see how we are going to find out the Gini index. So to calculate the Gini index of each attribute and to construct a decision tree, first we will start by analyzing the given data, and we are going to calculate the Gini index for each attribute as the first step. Okay. So here in this data set, if you see, we know that we have these are the four attributes we have, that is temperature, humidity, wind and outlook, and the last one is, already I told you, it is the class label. So outlook, just look at here what are the values in outlook, and temperature we have, these are the values. humidity, these are the values, and windy, these are the values. Play 10 is the class label is either yes or no. So these are the attributes to calculate the Gini index for the particular data set what we have taken as an example. Now steps to construct a decision tree using Gini index. The very first step is we have to calculate the Gini index for each attribute. Second one, I already told you, calculate the weighted Gini index for each attribute. So let us see in detail how we are going to calculate the Gini index as well as the weighted Gini index for each attribute. So first, the very first attribute in the data set is outlook. In that outlook we have three values. The very first one is the sunny. So in sunny, just like same like yesterday's example, like last class example, play equal to no, play equal to yes. We have no and yes. For sunny, total we have 5 values in the data set, 5 rows. In that 5 rows, no is having 3 and yes is having 2. Now, how we are going to find out the Gini index for sunny is 1 minus, just remember the formula, 1 minus P1 square plus P2 whole square. That is, once you apply negation, means minus inside, we will get the negative values. So here, you see here, so for yes we have 2 and no we have 3. That is 2 plus 3, 5 divided by whole square, and for no we have 3 and total number count is 3 plus 2, 5 whole square. So 2 by 5 whole square, we know that we get it as 4 by 25 and 3 by 5 is 9 by 25. So 1 minus this one, just we are going to get it as 12 by 25. So this is the Gini index for particular only one value sunny in the attribute or feature outlook. Similarly, the next one is overcast. Total we have 4 rows of overcast in that particular example. That is, no, we don't have any count, count is 0. But whereas coming to yes, the count is 4. So what is the formula for Gini index for overcast? Simply minus 1 by 0 by 4. Why 4? 0 plus 4. Total is we have only 4 rows. That's why it is 0 by 4 whole square minus 4 by 4 whole square. Something will get the answer it as 0. The next value is rainy. Now here in rainy we have total 5 rows in the data set. In that 3 is no and 2 is yes. So Gini index for this rainy is, we can say that 3 by 5. Why? Because 3 is no, 3 plus 2, 5 whole square minus yes is 2, 3 plus 2, 5 whole square. So when you calculate this, something will get it as answer as 12 by 25. Okay. Next, calculate weighted Gini index for outlook. Now we have find out the Gini index of each attribute. Now we are going to calculate the Gini index for outlook. That is, we know that here total, see here for sunny we have 3 plus 2, 5. Why I have taken 14 here? In a data set we have 14 rows. That's why the value is 4. And for sunny we have 3 plus 2, 5. Multiplied by this value, 12 by 25. Similarly, plus for overcast we know that we have values 4 and total rows is 14. Multiplied the value of this one, 0. Similarly, for rainy, we have 3 plus 2, 5 divided by total rows 14 into 12 divided by 25. That is in Gini index for rainy. Total we are going to get the value as 0.42. In this way, we are going to find out the Gini index for each and every single or separate attribute. Thank you.